Okay, can everybody see and hear me?
Check.
Yep.
Yeah, okay, good. All right, so introduction to algebraic vectors. Our learning goals today are going to be to learn to write a vector in algebraic form, learning to find the magnitude of a vector in algebraic form, and learning to draw an algebraic vector in 3-space by making it look like it exists in a 3-dimensional box. Okay, so it's hard to draw something on a piece of paper and make it look like it's in 3-dimensional space. So when we put it in a box, it will look more like it's in 3-dimensional space. Problems involving vectors can often be simplified by introducing a Cartesian coordinate system. First, we're going to look at vectors in 2-space because working with an XY plane is what you're most used to from grade 9, 10, and 11. So recall that a vector is defined by its magnitude and direction, so completely. So if you know the length of a vector and what direction it's pointing in, then you can completely define the vector. So we're going to draw the vector AB that starts at the point A, negative 6, 1. So negative 6, 1. There's my point A. And point B is at 1, 5. And join them. And there's your vector AB. And they want to know its magnitude. So you can see that I can make, to find the magnitude of vector AB, I could make a right triangle here. Here's a right triangle, so I could use Pythagorean theorem to find the magnitude of vector AB. So I could say the magnitude of vector AB squared is equal to, so this is 1, 2, 3, 4, 5, 6, 7, 7 squared, plus 1, 2, 3, 4 squared. So I square root both sides. The magnitude of vector AB is going to be the square root of 7 squared plus 4 squared. So exactly, it's going to be the square root of 49 plus 16, which is 65. So that's exact. And in algebraic vectors, we'll be doing things exact for the most part. So this will be where we would leave things most often with square root of 65. But we can also do approximate if we want to see approximately 8.1 units. So the length of this vector is square root of 65, or approximately 8.1 units. So now we're going to make what's called an algebraic vector. Algebraic vectors, their tail is always at 0, 0, or if we're in 3-space at 0, 0, 0. So its tail is always at the origin. So if we want to reproduce this vector here, vector AB, but starting at the origin, so here's our new starting point. Well, our new ending point, if we want it to have the exact same magnitude and direction, is going to be moved 7 to the right and 4 up from 0, 0. So 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4. So this vector here that starts at 0, 0, 0 is going to end at the point P. And P has the coordinates 7, 4. And let's draw that vector in. So again, its tail is at 0, 0. Its tip is at 7, 4. It's an algebraic vector. Algebraic vector OP. And we know P is 7, 4. So now we're introducing some new notation here. we asked what the coordinates of P were, we said 7, 4. But an algebraic vector is made by subtracting the coordinates of P and 0. So vector OP, we use round brackets to show an algebraic vector. And we're going to subtract corresponding x values. 7 minus 0 is 7. And 4 minus 0 is 4. So the algebraic vector OP is the vector. So when you see this ordered pair, you're thinking vector 7, 4, not 0.74. And the reason we know that is because we've got a point-to-point vector on this side with a vector arrow over top, so that this ordered pair represents a vector, not a point. And it represents the vector that starts at 0, 0 and ends at 7, 4. Okay, it's a point-to-point vector that starts at 0, 0 and ends at 7, 4. An algebraic vector in two space begins at the origin, like we said, and ends at a point pxy in the Cartesian plane such that vector OP is equal to xy. Okay, so vector OP is equal to vector xy. For vector little v, we can also use one small letter, is equal to vector v1, v2, where v1 is the x component of the vector and v2 is the y component of the vector. And it completely defines the vector. So knowing this, it's a different color here. If I know this, then I automatically know the vector starts at 0, 0 and ends at 7, 4. I have a way of finding its magnitude using Pythagorean theorem. Okay. I also, if I wanted to, could find its direction. If I considered the direction to be between the positive x-axis, if I just considered this to be the direction, I could find that as well using SOHCAHTOA trigonometry. So it completely defines the vector. I could get both its magnitude and direction just by knowing that it starts at 0, 0 and ends at 7, 4. So in the Cartesian vector pictured at the side, so algebraic vector and Cartesian vector are synonymous, they mean the same thing. Pictured at the side, it is important to know that the point AB represents a point, okay? And the origin 0, 0 is also a point, whereas OP equals AB is a vector, and we're calling that vector V. So in other words, we could have vector OP from O to P, and that's going to be A minus 0, which is A, B minus 0, which is B, or we could call that same vector, vector V, which is AB. And that's an algebraic vector. Okay, so kind of lots of definitional stuff here.
Ms. Northwood?
Yep.
I'm wondering, when you're writing down some of the points,
Yep.
and I think we've done this, you're able to write down the algebraic letter for the point, and then immediately after it, the coordinates.
Yeah, so that's a good point as well. So if, say, I was writing down the 0.34, that would be writing down 0.34. That does look like a comma, I hope, in there. But if all of a sudden I want to write the vector 34, I'm either going to use two capital letters with a vector over top, or I'm going to use one small letter with a vector symbol over top and an equal sign between them. Okay, so here's a point. This point just represents 1.34. OP vector represents the vector 34 that starts at 0, 0 and ends at 34, or vector V is the vector that starts at 0, 0 and ends at 3, 4. Okay, so again, communication is such a huge part of this, and thanks for clarifying that, John. Okay, so also given any algebraic vector AB with starting point, that's A, x1, y1, and ending point B, x2, y2. It's an algebraic vector such that AB is equal to x2 minus x1, y2 minus y1. Okay, so that kind of needs a little bit more explanation here. So I'm going to use this first example here and my whiteboard as an example for that. So it's saying that it's the vector that joins the points -3, 4. So -3, 4, I'm going to draw it on here. -1, 2, 3, 1, 2, 3, 4 is my point A. And my point B is 2, -2. So my vector would look like this. And I'll just quickly write on what point A was and point B was. So it's saying that if we want the algebraic vector that goes with it, we know that that's going to start at 0, 0. And we do know that if I wanted to reproduce this pink vector, I would go over 1, 2, 3, 4, 5 and down 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 1, 2, 3, 1, 2, 3, 4, 5, 6. So that should be my endpoint there for my algebraic vector. So it would have exactly the same, oops, yep, I can see that on my screen, so hopefully you guys can see it too. That should be my algebraic vector OP, if I want to call it that. But this point here, P, should be able to be found by doing B minus A. So 2 subtract -3 should be the X component of the ending point. And -2 subtract 4 should be the Y component, which is 5, -6. And this point here is 1, 2, 3, 4, 5, -6. Okay, and then since the vector starts at 0, 0, this vector here, if I wanted to call it little v, would be vector 5, -6. So that's what this is saying, and it probably looks more complicated here. But if you want to find the algebraic vector between 2 points, you subtract the corresponding X components and subtract the corresponding Y components, and then you'll get the vector that starts at 0, 0. And so that then is an algebraic vector. So if I want vector AB, then we just prove that it's going to be vector AB is B minus A, so 2 minus -3 is 5. -2 minus 4 is -6. Again, that means the vector from 0, 0 to the point 5, -6. And the magnitude of vector AB, if I come back over here to this whiteboard here, again, I could make a triangle and use Pythagorean theorem, which is that formula is basically doing for me. And I would see that this is 1, 2, 3, 4, 5, 6, and this is 5. And it's just going to be the square root of 6 squared plus 5 squared by the Pythagorean theorem. So the magnitude of vector AB is going to be the square root of 5 squared plus, now when we're just starting, I'll put -6 in brackets squared, but I don't even mind if you don't include the negative sign, because I think you know, I want you to know in your heart that when you square a negative number, you get a positive. So this is really the square root of 25 plus 36, or the square root of 61. So the length of this vector, I'll show you one more time here, the length of this pink vector or this blue vector, which is the algebraic vector, is the square root of 61 units, which is approximately 7.8 units long. Okay. So we're just doing that, we're practicing doing that then. So given 2 points, how do we make the algebraic vector? So if our starting point is A and our ending point is B, we do B minus A to get our algebraic vector. So 5 minus 0 is 5. 6 subtract -4 is positive 10. And then the magnitude of that vector that starts at 0, 0 and ends at 5, 10 is going to be the square root of 5 squared plus 10 squared, or the square root of 125. And we're going to leave them as square roots unless it's a perfect square. So for the third one, vector, algebraic vector AB is going to be 2 subtract -8, which is 10. -5 subtract 3, which is -8. And the magnitude of it is going to be the square root of 10 squared plus, well, I know when I square a negative number, I'm going to get a positive answer, so I could just write 8 squared here. So the square root of 164. And then here, we're already given an algebraic vector because they're starting at 0, 0. So AB is just going to be 7, 2. 7 minus 0, 2 minus 0. The magnitude is going to be the square root of 7 squared plus 2 squared, which is the square root of 54. No, 53. Square root of 53. All right. So I'm going to give you a little hint of what you're going to do in your second video today. So imagine how easy it would be to add vectors. We added vectors geometrically the last time I saw you using trigonometry. Now look how easy it is to add algebraic vectors. So if vector u is the vector 2, 1, it means it starts at 0, 0 and ends at 2, 1. This is really cool. Pretty exciting. I hope you find it exciting too. So there's my vector u. I'm going to draw my vector v, which is 3, 4. So starts at 0, 0 and ends at 3, 4. So if I want to find vector u plus v, I know I add them tip to tail. So here's my vector u in pink. So to put vector v at the tip of it, because you add vectors tip to tail. So I'm going to reproduce vector v, which is over 3, 1, 2, 3, and at 4, 1, 2, 3, 4. So there's vector v on the tip of vector u. And then this vector from 0, 0 to the tip of vector v is going to be vector u plus v, this orange vector I just drew. And we can see that vector u plus v is going to be algebraic vector 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. This point here is 5, 5. So vector u plus v is 5, 5. Now watch this. Without any diagram, vector u is 2, 1 plus vector v, which is 3, 4. So vector u plus vector v, add the x components, 2 plus 3 is 5. Add the y components, 1 plus 4 is 5. Algebraic vector u plus v is 5, 5. So that's pretty cool, I hope you think. No trigonometry involved. If you wanted the magnitude of vector u plus v, all you would need to do is the square root of 5 squared plus 5 squared, which would give you the square root of 50. So that's what's coming this afternoon, or in the second video, is operations with algebraic vectors. Okay, so algebraic vectors can be seamlessly extended to three-dimensional space. an algebraic vector in 3 space from the origin to a point P, X, Y, Z can completely be defined in Cartesian form by the vector OP equals vector X, Y, Z. So this diagram depicts the vector OP, or vector little v, equaling vector ABC. It starts at the origin, O0, 0, and ends at the point ABC. So again, I'm showing you 3 space and 2 space. It's kind of hard to visualize. I'm going to use my whiteboard for a second and just reorient you to what happens when we shift to 3 space in grade 12. So in 3 space, up is the positive z-axis. Okay, so that's a shift for us. We're used to y being up and down, but when we shift to 3 space, z is up and down. So positive z-axis is up, negative z is down. The y-axis is left to right, so right is positive, left is negative. And then we add the x-axis, it's coming out at you, out of the page at you. The positive x-axis comes out of the page at you, and the negative x-axis goes into the page. So now we're in 3 dimensions, okay? It's hard to draw 3 dimensions on a piece of paper, but that's what we're going to try to do here, okay? So this vector then starts at 0, 0, 0, which is here. So here's my origin, and that's where the x, y, and z axis all intersect. That's the point O, 0, 0, 0. And then to get to this point here, I've come A along the positive x-axis. So this distance from here to here is A. Then I've gone B in the positive y direction. And then I've gone C in the positive Z direction. And that gets me up to this point in the top corner of the box that you see there. And the vector is being joined from O0, 0 to the point P, ABC. Okay? And it should look like it's in a box, and therefore it should look more 3-dimensional. And what I want to show you from the diagram is that if I wanted to find the magnitude of this vector, it would simply be the square root of a squared plus b squared plus c squared. So I'm going to start off by saying that first we're going to find this diagonal here. So if I just want that diagonal, it's hard to see here, but we know that if this is the x-axis and this is the this is the x-axis and this is parallel to the y-axis, then this is a right angle here. So that's a right angle triangle. So I'm going to call this O, and I'm going to call this point over here D. So if I want the magnitude of OD vector squared, I can use the Pythagorean theorem. It's going to be little a squared plus little b squared. Okay? Keep that in mind. So now I want the magnitude of vector OP. And I'm going to, again, I can use the Pythagorean theorem here because this is flat and then this is straight up and down. So it's like having my flat and then straight up and down. There's going to be a 90-degree angle between this pink pen here and the white ZY axis I have there. Okay? Which means that this is a 90-degree angle here, even though it doesn't look like it on flat paper. So vector OP is my hypotenuse, and I can use Pythagorean theorem. So the length of vector OP squared is going to be the length of vector OD squared plus this distance here squared, which is c squared. However, we just said above that vector OD squared was the same as a squared plus b squared. So vector OD squared is A squared plus B squared. And then we still have our plus C squared. Square root both sides to get the magnitude of vector OP by itself. We're calling the magnitude, or we're calling vector OP vector V. So the magnitude of vector V is just the square root of A squared plus B squared plus C squared. Really super easy to find the magnitude of a vector in 3 space as long as you know the 3 components. Very easy calculation to be done. Okay, so sketch each of the following vectors in 3 space. Determine the magnitude of each vector. All right, so for some people every year, some people find this super easy, and then some people are like me and they are not good at seeing things before they appear to them, and drawing isn't their thing. So I have a method that works for everybody. So I've got these axes that I've made. So I just took a regular X, Y axis and changed it to a Z, Y axis. Okay, so Z again, positive Z is up, positive Y is to the right, positive X is out of the page, which is, that's the way I'm drawing it in 3 space. So I chose a diagonal. And what I did to get how far these tick marks are apart was I measured with a ruler how long one of these squares was. And then I started at 0, and then every, I think it was 4 millimeters, I drew one of these tick marks. If you're gonna have to draw one for yourself today for the assignment, there's one vector in a box that you have to draw. Okay, so that's how I made my X, positive Y, positive Z axis here. So this is my method for drawing. First, we're gonna draw the box and then we'll draw the vector. So the first thing I do is I remember that this is really X, Y, and Z, right? That's my ordered triple, we'll call it. This is an algebraic vector in 3 space. So what I do is I ignore X for a moment, and I just focus on drawing the rectangle involving Y and Z. So positive 6 in the positive Y direction from 0, 0, 0, which I know that's where I know my algebraic vector is going to start, would be over here. 1, 2, 3, 1, 2, 3, 4, 5, 6. And I know that 5 in the positive Y direction is up 5. 1, 2, 3, 4, 5. And I want to make a rectangle out of that. So from my over 6 here, I'm going to go up 5. 1, 2, 3, 4, 5. And from 0, and then I'm going to take a ruler and draw that rectangle. And that's going to be, depending on X, either the front or the back of my box. If X is positive, it will be the back of my box. If X is negative, it will end up being the front of my box. Okay, so in our case, X is positive 4. So once you've got the back of your box drawn, you're going to use X now. So X is positive 4. So from 0, 0, 0, you're going to go along the positive X axis 4 hash marks. So 4 spaces. 1, 2, 3, 4. And then I'm going to draw my dot in there. And it's not going to be right on the corner of the ZY plane, usually. Okay, it's going to be somewhere floating somewhere. To keep that in mind. So from this is going to be a corner of the front of my box. I want to then go up, because Z is up and down, and we have a positive Z, so up 5 from here. So this looks like it's just in the corner of this box here. So up 1, 2, 3, 4, 5 puts me just in that corner. And then I want to go from here, 6 in the positive Y direction. So right 6, 1, 2, 3, 4, 5, 6. And then again, from this corner, I want to do my up 5 again. So I've made a rectangle. So once you've got the 4 points for the front of your box, you're going to get your ruler out and make the front of your box. So I'm joining these points together, with a ruler. So now I've got the front of my box drawn and the back of my box drawn. So now you join the corners. So I join this corner and this corner with a ruler. I join this corner and this corner with a ruler. This corner and this corner with a ruler. And this corner is right along the x-axis always. So it doesn't show up as much, but I'm joining them. So that's my three-dimensional box. So that box looks like it comes out of the page. So now I want to draw on my vector. So I know my vector is going to start at 0, 0, 0. So right where the three axes meet, that's my starting point. And then I know to get to my ending point, I'm going to go first 4 in the positive x direction. Maybe it's better to use a highlighter. I don't know. Can you see that? No, that doesn't really show up. I'll use my highlighter here. So I'm going to go from 0, 0. I'm going to start off going 4 in the positive. You still can't see that very well. There you go, 4 in the positive x direction, followed by 6 in the positive y direction, followed by 5 in the positive z direction. So right there in the front right corner of the box is going to be my ending point for my algebraic vector. And then I want to get my ruler out and join the origin to that front right corner, top right corner box of the box. And put an arrow on the end. There's my arrow. And then I'm going to call this, they want me to call it vector V. So this orange vector is vector V. And it should look like it's in 3 dimensions. Like it's coming out of the page towards that top corner. So I did all that work just to draw the vector so that it looks like it's in 3 dimensions, which is a course expectation. Now I just need to find its magnitude, which is easy. So the magnitude of vector V we know is going to be the square root of 4 squared plus 6 squared plus 5 squared. Or the square root of 77. And I'll just keep it exact. So that's the length, the magnitude of that vector. All right. Next one. The vector from the origin O, 0, 0 to the point Q, 3, -2, -4. So first let's make our algebraic vector. So it's going to be vector OQ, which is going to be 3 - 0, -2 - 0, -4 - 0. So there's the vector we're going to draw. We know this is our x component, y component, z component. So we're going to start off making our rectangle according to y and z. So this time we're going from 0, 0, 0 to -2 in the y direction. So that's over here. And also -4 in the z direction. So that's down 4. 1, 2, 3, 4. And then we'll make our rectangle using a ruler. So that's going to be the back of our box because x is positive. So once we have the back of our box drawn, we're going to go along our x-axis, in this case, +3. So from 0, 0, 0, 1, 2, 3. So there's a corner of the front of our box. It looks like it's on the back of our box, but that's where it is. That's where it lands. Maybe I'll do that in a different color so you can see it more clearly. Use pink. So there's my corner there. And then I'm going to go 2 to the left in this case. So 1, 2, and down 4. 1, 2, 3, 4, and 1, 2, 3, 4. So those are the corners for the front of my box. So I'm going to join them together to make the front of my box. And then once you've got the front and back of your box drawn, then you're going to join corner to corner. One's always going to be along the x-axis. And then you'll have your box drawn. So that should look like it's in 3 dimensions. And you know that your vector is going to start at 0, 0, 0. And it's going to end at, from 0, 0, 0, you're going to go +3 along the x-axis, followed by -2 in the y direction, followed by -4 in the z direction. So we're going to end up in the bottom left corner, front bottom left corner. And then you're going to join the origin to that point with a ruler and an arrow. And then label it vector, in this case where it's a point-to-point vector, vector OQ. And since it is, I'll probably label point O there and point Q down here. And then this is vector OQ. O for origin, Q for the point 3, -2, -4. And try to make your arrow as seeable as possible. Okay. And then another one, so we've got vector u equals -3, -4, -5. So again, ignore x for now and draw the rectangle involving y and z. So we've got -4 for y. So that's left, 1, 2, 3, 4. And +5 for z, 1, 2, 3, 4, 5. So then we're going to draw in this rectangle. Oh, you know what I forgot to do? I forgot to find the magnitude of the last vector, so I'm going to go back and do that after I've drawn this rectangle. Okay, so we need to find the magnitude of vector OQ, so that you write that like this. The magnitude of vector OQ is equal to the square root of 3 squared. You could write -2 squared like this if you want, or if you know that squaring a negative number is going to give you a positive number, I'll do that for the z component. You can just write 4 squared and ignore the negative, because you know in your heart that when you square a negative number, you're going to get a positive number. So the magnitude of that vector is going to be 16 plus 14, square root of 29. All right, so back to C. We've drawn either the front or back of the box. Now in this case, it's going to end up being the front of the box because x is -3. So from 0, I'm going to go 3 in the negative x direction, which is into the page, 1, 2, 3. So there's going to be a corner of my box. right here. So from that corner, I'm going to apply -4 in the y direction. So I'm going to go over from here, 1, 2, 3, 4. And then up, because z is positive, 1, 2, 3, 4, 5. And those 4 corners are going to be the back of my box. And then I'm going to join the corners of my box. Okay, and we know that our vector is going to start at 0, 0, 0, the origin. So be careful that you're finding the starting point is where the 3 axes intersect. Can get confusing. And then you know that the end point is going to be once you've gone -3 in the x direction, followed by -4 in the y direction, followed by 5 in the z direction. So up in this back, top, left corner. And then we join the origin to that end point. There's our vector. Make sure you show an arrow clearly. And then this vector is getting labeled vector u. Okay, so we've practiced 3 times drawing a vector in a box. Any questions about this? Can you still hear me?
Yep.
Yeah, we're good.
I'm wondering, will we always have that like x-axis line like that?
Well, if you print out my handouts, yes. Okay, so the only way you would have to make this is if you don't have a printer, which I know some people don't. Some people picked up handouts last week, which is great. If you're making it yourself again, I would start off with graph paper if you possibly can, and then measure, like if I take my ruler and measure a square here, it's giving me, this one's actually giving me 4.5 millimeters. And then starting at 0, 0, every 4.5 millimeters along here, I would put a tick mark. Okay, that's how I would make my x-axis at a 45-degree angle.
I'm wondering, would we ever want to set the axes on that sort of like dot paper that's like 30 degrees?
The orthogonal paper?
Yeah.
You could do that. Your vectors look skewed because they don't. Actually, I think dot paper, they don't. They look okay. It's the only way is if you make your x-axis, what do you call them, hash lines, a lot farther apart than your y or z, and then it looks distorted, but it's okay. However you can do it to make it look 3-dimensional, I'm okay with, especially in this remote system. Hopefully we'll be back at school soon. This is a small thing. It's just one expectation. We're going to take care of it today, and then we won't really be drawing them for the most part. We'll be imagining them. All right, so if a vector in 3 space begins not at 0, 0, but at any other point and ends at a different one, then you can get an algebraic vector the same way you could in 2 space by just subtracting, in this case, b minus a, corresponding x coordinates, y coordinates, and z coordinates. So we'll fill this chart out here. If we want vector AB, remember vector AB is b minus a. So vector AB is going to be 5 minus 7, -2, vector -2. 3 minus 1 is 2, -5. So the vector that starts at 7, 1, 2 and ends at 5, 3, -3 is the same as a vector that starts at 0, 0, 0 and ends at -2, 2, -5. Okay? And the magnitude of that vector is going to be the square root of, so I know that when I square a negative number, I'm going to get a positive, so I could just write 2 squared plus 2 squared plus 5 squared, or the square root of 33. And then our next vector AB is going to be the vector that starts at 0, 0, 0 and ends at 1 minus -4, which is 5, 2 minus -1, which is 3, 1 minus 3, which is -2, and its length is going to be the square root of 5 squared plus 3 squared plus 2 squared, which is going to be the square root of 38. Here, vector AB is going to be the vector that starts at 0, 0, 0 and ends at 4. 10 minus 1 is 9. 7 minus 3 is 4. Ends at 4, 9, 4. So vector AB is vector 4, 9, 4, and its magnitude is the square root of 4 squared plus 9 squared plus 4 squared, which is the square root of 113. And here we start at 0, 0, 0, so it already is an algebraic vector. -5, 2, 1. Which has a magnitude of square root of 30. Okay, so that's how you make algebraic vectors if you're given a starting point other than 0, 0, 0, just endpoint minus starting point. So here's an example. A vector has initial point A 3, -4, 7, and terminal point B 5, 0, 11. Find vector AB. So vector AB is B minus A, which is 5 minus 3, 0 minus -4, 11 minus 7. Vector BA. So now we're starting at point B and ending at point A, so it would be A minus B, end point minus beginning point. So that's going to be 3 minus 5, -4 minus 0, 7 minus 11. What do you notice about vector AB and vector BA?
They are opposite each other.
They're opposite, right? Each component is got the opposite sign. Each component has got the opposite sign, so they're equal in magnitude and exactly opposite in direction, which is hopefully what you would expect. Now they want the magnitude of vector AB. So the magnitude of vector AB is going to be the square root of 2 squared plus 4 squared plus 4 squared. So that's going to be the square root of 38. And then part D, they want a unit vector in the direction of AB. So one thing you have to know is this isn't a thing. You can't write that. Okay, that's not an acceptable vector notation. So you have to choose a small letter. So I'm going to choose U. U hat then is going to be vector AB. So to find a unit vector, you always take the vector and divide it by its magnitude.
Miss Northwood?
Yep.
I believe the magnitude for AB should be 6.
Did I add wrong here? 32 and 4, you're correct, is 36. Thank you. And square root of 36 does turn out to be 6. Lovely. Okay. All right, so our unit vector U hat is vector AB, which is 2, 4, 4, over 6. And we can think of that as 1/6 times vector 2, 4, 4. And we can multiply a scalar by a vector using the distributive property. That was a vector property we learned a week and a half ago. So 1/6 times 2 is 2/6. 1/6 times 4 is 4/6. And 1/6 times 4 is 4/6. And then in this case, we can reduce those components. 2/6 is the same as 1/3. 4/6 is the same as 2/3. And 4/6 is the same as 2/3. So a unit vector in the same direction as vector AB would have components 1/3, 2/3, 2/3. So it would have exactly the same direction as vector AB, but it would only be 1 unit long instead of 6 units long. Okay? In exactly the same direction. That's what a unit vector is. Okay, I don't expect you to show this step. If I was doing this, I'd just think, okay, well, I can do go to 2, 6, 4, 6, 4, 6, which is this line here, and then see if there's any reducing I can do in this last line. You don't need to show this step, but I am, because it's the first time we've done it. Okay, and our last question for this morning. Determine the unit vector, another unit vector question that is in the opposite direction of the vector AB. So we talked about how we get opposite direction. Let's call it vector V. What would vector V be if it's got the opposite direction of vector AB?
We'll have the opposite signs in all the axes.
Right, all of the opposite signs in all of the components. So -5 for the X component, +5 for the Y component, +2 for the Z component. So there's a vector that's the opposite direction of vector AB, but we want a unit vector. So our unit vector formula, V hat is going to be vector V divided by its magnitude. So we take a vector, divide it by how long it is, and we'll get a vector that's 1 unit long in the exact same direction. That's the theory. So vector V is -5, 5, 2. Its magnitude is going to be the square root of 5 squared plus 5 squared plus 2 squared. Which is the square root of 2554, which is not a perfect square. So V hat vector is going to have components -5 over the square root of 54, 5 over the square root of 54, 2 over the square root of 54. So remember, this is a vector with a magnitude or a length of 1 unit in the same direction as V equals -5, 5, 2. So it's a vector with a magnitude of 1 in exactly the same direction as vector V. That's what a unit vector is.
Miss Northwood?
Yep.
I'm wondering, when we're getting the magnitudes of the vectors, and we'll end up with like radicals a lot of the time. Is it good to simplify those like a little bit sometimes? Like say if you have square root of 50, to have 5 square root 2 or something like that?
Yes. So you'll find sometimes that will be done and sometimes it won't. I can't find a tried and true rule of when they do it and when they don't. For the textbooks we use in grade 12, I find like once you get, you move forward, they make nice numbers on purpose just so that you can do calculations quickly. But yeah, there's, if you want, John, I totally approve of you changing that to root of 9 times 6, and you can do this all in your head, but calling the denominator 3 root 6, there's no real advantage to it unless there's some more simplifying you can do there. And if you can see in the numerators, if our denominator is 3 root 6, it doesn't really help us simplify the numerators anymore. Okay, but I'm okay if you just like doing it. Like I like doing it too, and at first I was always doing it, but then no one was getting the answers in the back of the textbooks when we were using the textbook all the time. And I noticed they just left it 90% of the time. And then as you said, when it was something like root 50, they would change it. So it's up to you on that. I don't mind either way.
I guess just sometimes you might be able to simplify.
Right. If you see on the bottom and go, okay, well, I can reduce this and make it a lot simpler looking, then yeah, sure, do it.
Okay.
Okay, so this morning, I hope that you were able to write a vector in algebraic form, so you know that ordered pair form, ordered triple form, how to write an algebraic vector given its starting point and end point. You can find the magnitude of a vector in either 2-space or 3-space algebraic vectors. And you can draw an algebraic vector, make it look like it's in 3-space by making it look like it exists in a box. Okay, so I'm going to stop recording now and go back. Stop recording.